Hello everyone, it's 6 o'clock. We'll wait for 5 more minutes, I guess, for others to join. Then we'll start today's class. Yeah. Sorry, good evening everyone. We'll start today's lecture. Do you have any doubts or any questions regarding the previous class? Do let me know. or else I'll share my screen now. Are you able to see the screen? Can anybody please confirm? Are you able to see my screen? Okay, thank you. So today is the sixth lecture of this material characterization course, which is provided by Dr. S. Sankaran from IIT Madras. And here am I, Dorothy Sachdeva, your PMRF TA, and I am doing my PhD at MRC department at Indian Institute of Science, Bangalore. So in the previous lectures we have learnt about the optical microscopy, and then we learnt about the SEM techniques. From last two lectures we have been studying about the SEM and how the different electrons from the SEMs can give you information depending upon your requirement. And there is one more SEM technique which was left, that is the electron backscatter diffraction, which is generally known as EBSD patterns. These are basically just a representation of the Kikuchi diffractions. And what is the Kikuchi lines? Kikuchi lines are basically the inelastic scattered electrons which can subsequently be elastically scattered by the lattice planes to produce the phenomenon known as Kikuchi lines. So firstly the electrons undergo the inelastic scattering, and then it undergoes the elastic scattering, and the resultant of these two gives us the Kikuchi lines, which have two parallel lines, one with a very light color and other is the dark color. Kikuchi lines will be best seen in the diffraction pattern from areas of the specimen that have low density of defects and are about half the thickness that the beam can penetrate or thicker. So these Kikuchi lines will not be visible if your sample is very thick or if your sample is very thin. These Kikuchi lines will be visible only in case where the thickness of your specimen will be about half that the beam can penetrate. So the thickness is considered when you are able to see, the thickness of the sample will tell if you are able to see the Kikuchi lines or not. If the specimen is thinner, only spots will be seen. If it is very thick, only Kikuchi lines will be seen. So thickness of the sample plays a major role to find the Kikuchi lines, and Kikuchi lines basically represents your EBSD pattern. So the Kikuchi lines looks like this, where Kikuchi lines are basically just the roadmap. Basically we will discuss, I guess, this in later lectures. I'll explain you in much more details about these Kikuchi patterns in TEM part. Here I just only wanted to say you that these are the Kikuchi lines, this line, this line, and the intersection of these lines. Like consider this point A. Let me make it point A. If this is point A, then you can see various number of Kikuchi lines which are intersecting at these points, like this horizontal one, this one, vertical one, these diagonal ones, the broader one, these smaller one. All these are intersecting at this point A. So all these are the Kikuchi line, and point A is known as the, which is the intersection of all these lines, is will be known as the zone axis of these planes. This each line represents different kind of planes. For example, there is another zone axis which I am representing by this point B in this Kikuchi pattern. So at this point B and point A, both are zone axis, that they will represent different zone axis. Here different kind of planes. These lines represent basically the planes. So at point B, different planes are being intersected, and point A, and at point A, different planes are intersecting. So intersection of different planes at point A represent one zone axis, and at point B it represents some different set of different set of planes with different zone axes. Similarly, they are extended in all two dimension, and as you will go from point B, then as you will follow this, the diagonal one, this, if you will follow this plane, then you will go to another zone axis which is not halfly visible in this Kikuchi pattern. So this is another zone axis. So these are basically, the Kikuchi patterns are basically the road maps which will tell you where to go. If you want to specifically go to a specific zone axis, then you can follow. Once you are able to see this Kikuchi pattern, then you can follow these patterns and you can go according to your requirement. These patterns we will discuss later on, how major contribution of these Kikuchi patterns are will be discussed in the TEM part. But here also the EBSD represents the Kikuchi line patterns only. So how these Kikuchi lines are formed? So if this brown one is your specimen and this yellow one is your incident beam, then when incident beam falls on the specimen, they, after the interaction with the specimen, with the lattice planes of the specimen, there are two rays, ray 1 and ray 2. So the ray 1 is a closer to the forward direction than ray 2, so it is more intense, and an excess number of electrons over the background will arrive in the back focal plane. So you all know, if not then I am telling you that the Kikuchi, the diffraction is basically formed at the back focal plane. There are two kinds of plane. One is the image plane and one is the back focal plane. Back focal plane is the one plane where the diffraction pattern is formed, and the image plane is one where the image is formed. This will also come in great detail in the TM part, but for the introduction and for the sake of how the Kikuchi lines are formed, I am just telling you that the diffraction patterns are formed at the back focal plane of the specimen. So the ray 1 is closer to the forward direction, so it will be more intense as compared to the ray 2, this blue one. So as a result, this will be more intense and the ray 2 will be less intense, and as a result there will be deficiency of the electrons at point D, and at point B it will be more intense. So there is a bright light at point B and a dark line at point D in the diffraction pattern. So a bright light and a dark line together will compose of one Kikuchi line. And depending upon the planes which are diffracting these incident beam, you will have different distance of these Kikuchi lines. For example, as you have seen in the previous Kikuchi pattern, some of the Kikuchi lines are very thin, like the line which is connecting point A and point B. But from point A you can see that the diagonal one are very thick as compared to the other ones. So depending upon the planes in which, through which they are being diffracted, they will have different, basically depending upon the D spacing from which they are being diffracted, they will have different thickness. I guess someone is in the lobby. Yeah. So how are these Kikuchi lines are basically formed? The diffracted rays, which are actually these basically form a cone kind of structure, and when this cone is interacted with your evolved sphere, it will form a straight line. So basically I guess I have, yeah. So the diffracted rays actually forms from the cone of a semi-angle 90 minus theta called the Cosel cones. This you can remember that these cones are known as the causal cones. So what we see in the diffraction pattern is pair of parabolas where the cones intersect the evolved sphere. The parabolas appear as straight lines in the diffraction pattern because the angles involved are very small. You can see in this one that when incident beam fall on the specimen, this red one is your specimen and this white one is your incident beam of electrons, and when these form on the specimen, they form these cone kind of structures on both the sides of the specimen, and these are known as the causal cones. And when these causal cones interact with your evolved sphere, then you will have this parabola, these light blue color lines. These light blue color lines when fall on the are projected on the screen, which are known as the Kikuchi lines. And in this, one Kikuchi line will be lighter and one Kikuchi darker, and one Kikuchi line will be brighter. So these together will form the Kikuchi line. So these are basically just the interaction of the causal cones with the evolved sphere. These are basically in the parabolic shape, but we are seeing the straight line because the angles are very small in this case. So the pair, it is basically Kikuchi lines are basically the pair, no? One will be the brighter one and one will be the darker one. So the plus minus G pair of the lines and the region between them is known as the Kikuchi band. The angular separation of the pairs of line is 2 theta. Their spatial separation in the diffraction pattern in the back focal plane is G, and the lines are perpendicular to G vector. Each reflection has an associated pair of Kikuchi lines attached to each. So basically what they are saying is that when the incident electron beams falls on the specimen, firstly these causal cones will be formed, and when these causal cones will interact with your evolved sphere, I guess most of you must have been knowing from the crystallography course. Have you taken the crystallography course? Do all of you know about the evolved spheres? Okay, okay, thank you. So when these causal cones will interact with your evolved sphere of your specimen, then they will form these Kikuchi lines, and then these Kikuchi lines is represented in this in another form, like this orange one is your incident electron beam, and your two due to your causal cone interaction with your evolved sphere, you will get these, one will be the excess line and one will be the deficient line. So these together green lines will form your Kikuchi band, and these Kikuchi band will form in the diffraction plane. So basically I told you that these Kikuchi lines represents the planes. Like if you want to go from this 111 to some other zone axis, then you want to follow some plane, and then you need to tilt your specimen. Tilting your specimen and all these things will come in the TM part. So basically these are the road maps which will tell you where to go if you want to go to certain zone axis. If your defects are only in certain direction, in certain orientation, then you need to see them in that orientation only. For that you need to have the specific orientation of your sample, and for that orientation thing you require this Kikuchi maps. Kikuchi lines and Kikuchi maps, what are their uses, are one of the most important aids which we have when we have to orient our specimen, or the identification of orientation in specimen is essential for any form of quantitative microscopy. So basically when you have defects in your sample, or when you have ordering anything like that in specific, or when you want to see the grain boundaries or anything which you have incorporated in your specimen, then you need to have certain zone axis from where you will look at, and for that zone axis you require these Kikuchi bands. So basically the Kikuchi lines consist of the excess line. One is the excess line and one is the deficient line. And in the diffection, it are formed in the diffection plane. And the excess line is further from the direct beam than the deficient. The excess line is further from the direct beam than the deficient line. The Kikuchi lines are fixed to the crystal, so we can use them to determine the orientations actually. The trace of the diffracting planes is midway between the excess and the deficient. So is this clear to you? So basically what is there in the Kikuchi lines, that one, the dark line will form, and one, the bright light will be formed, and those two lines will be formed by the interaction of your causal cones with your evolved sphere. And when this evolved sphere interacts with your causal cone, they will form a parabola. But we are able to see only the lines due to the small angle, and due to that small angle there are different type of lines, and the lines represent your planes, and these planes, your Kikuchi bands, will interact at, and when the interaction at certain point, and then that point is known as the zone axis, and you can use them as a roadmap to orient your specimen in certain direction and then do the imaging. So basically this sir taught you in this week's class. Also I wanted to add certain more things like EBSD technique, what it is used for. This technique is a technique which is used for the crystallographic orientation, for the misorientations. This is used for the texture trends. This is also can be used for the when you have different phases in your specimen, or these can be used for the grain boundaries, grain sizes, and all these things. In all these things your EBSD technique can be used. So basically these Kikuchi lines were observed firstly in the TM in 1928. This is a long back. And after that in 1954 these patterns were obtained by the LM in TM. And then later on these patterns were recorded in the SCM very later as compared to the TM. So these patterns are observed both in SCM and TM, but firstly they were observed in the TM. And we will, when we'll study TM, we'll also study its importance in the TM pattern analysis and TM pattern imaging. Then later on in 1980s these patterns were imaged with low light TV cameras, and in 1990s the automated pattern solving using the Ho transformation, and present day we can use them for the crystal orientation, for the local orientation and the misorientations, and for the grain boundaries, and for textured and for grain sizes, everything we can use the EBSD technique. So this was just the basic history of your EBSD technique. And later on the principal system components for this are the here the sample is placed. This is our stage, and your sample is firstly tilted at a certain angle which is 70 degree from the horizontal axis. So this is your horizontal axis. Your sample will be tilted like 70 degree from your x-axis, and then you have your very sensitive CCD camera, and all these things will be under a very high vacuum, and then there will be a vacuum interface for mounting the phosphor and camera in the SCM port. This is just basically the addition in your basic SCM technique. We have already studied the basic SCM technique, so this is just the extension of your SCM, where you can add your phosphor and the camera in the vacuum itself to get your EBSD patterns. And the for, and basically one thing is that you need to tilt your sample to 70° to get your EBSD pattern. And basically how are the patterns are forming? The high energy electrons, which are firstly which are elastically scattered by the atomic planes in the crystallographic sample. So basically this is your electron beam which is falling on the sample, and this sample is tilted at a 70° angle. So then after the diffraction you have this phosphor screen present at a certain distance, and then after that from the phosphor screen the intensities are being detected by this camera, and after this camera we have a computer from which we can analyze our sample. And I have already told you that when electron beam fall on the specimen, it will form a cosal cone, and the interaction of the cosal cone with the evolved sphere will give us the parabolas, which will look like straight lines. So these patterns are formed on your phosphorus screen, which are basically your Kikuchi patterns. So these are basically collected at a 70° angle. Here the beam current will be between 1 to 15 nanoampere, and the working distance of your specimen will be 10 to 25 mm, and the accelerating voltage is higher as compared to your SEM imaging, that will be between 15 to 30 kilovolt. So the EBSP, which is the electron backscatter diffraction pattern, will basically we have shown you for the silicon single crystal. So as you will rotate your specimen, your Kikuchi band patterns which you are seeing on your phosphorus screen and then on your computer screen, it will change. So as your sample is rotating, the pattern changes. So at 0° tilt, your Kikuchi pattern will look like this. If your Kikuchi pattern look like this, and then you tilt your specimen to certain degree, then your Kikuchi pattern will also move. As you can see, initially I'll mark the initial point so that you can see very clearly. So this O is your initial point which was at the center, but after tilting your point O has moved at this location, and after again tilting to 10 degrees it has moved to a certain far distance, and it is getting displaced as you are tilting your specimen. And at 20° you can't see that O point of your Kikuchi pattern, and then at 25° you can see that certain other zone axis is being come at the center, and then your sample is oriented in different direction. So similarly, when you are tilting your specimen, your sample is tilting and the orientation is changing, and as a result the Kikuchi patterns which are formed on the screen will also change, and they will tell you in which orientation you are basically present in. So basically this is one example of your EBSD pattern where these different colors will represent the different orientation. So basically these EBSD patterns, they come only from 20 nanometer surface area. So basically they won't go very deep inside the specimen. They will only come from the very surface, not very deep but very upper surface only. So this is very a surface phenomena we can say, where each grain will contain the specific orientation. So this dark blue color you can see, so this whole grain is in specific orientation, and then next grain the orientation is being changed as compared to the previous one, this one. So this gives you the colored maps of your EBSD pattern. So the one EBSD pattern looks like this, and where your color, which plane will be represented, there is one palette from where you can see that the dark blue one will be 111 plane oriented, and as the color is changing, your plane orientation will also change. So it gives information about the boundaries like the twins and all, and also about the orientation of your specimen. So basically your EBSD is used for the quantitative measurements, for the microstructural data, for the phase identification, for the strain analysis, and for the mapping as well, for different orientations. So in summary, the EBSD has become a well established microstructural analytical technique. The EBSD mapping can be used to explore the processing, microstructure, property relationships. EBSD can be used on most crystalline materials. The grain size, the sample tilt, the sample preparation are the primary limitations of the techniques. The sample preparation, because you should have a specific thickness of your specimen to have the Kikuchi pattern, and for that you need to have certain sample preparation techniques which will, and the sample tilting, you need to have a very high degree, that is 70-degree tilt in your specimen to get the EBSD pattern. So this was all for today. So if you have any doubt in the theory, then please let me know.
But we can apply this method only for thin film only.
You need to have sample preparation. It will basically, it will tell you about the sample information only from the surface only. You can apply it to see your Kikuchi lines. You need to have a thin specimen, and for that you can not have a very thick specimen. In very thick specimen you will not be able to see your Kikuchi patterns. After seeing the Kikuchi patterns only, you align your sample in certain orientation, and then you see your the features from which you want to analyze your sample. Any other questions? Everything else is clear to everyone? If yes, then we'll go to the questions of this week assignment. I guess there was only one assignment, no? Have anybody checked? Earlier, from the last 5 weeks, I was able to see two. One was the practice and one was quiz. But this time I was able to see only the quiz. Am I right? Okay. Okay then. I have certain few other questions that we'll discuss after this quiz is being done. Just for your understanding of your EBSD. So what is the minimum grain diameter for EBSD imaging? Grain diameter. Grain diameter for your EBSD imaging. Due to the tilting, you cannot have a very high dimension of your specimen. So the answer of this question is 10 nanometer. Option B. The second question says that the spatial resolution of the EBSD is about to dash. Statement 1 says for high resolution imaging on nanograins. This statement is correct or wrong? They are asking about the spatial resolution of the EBSD. Spatial resolution, you can correlate this with your SCM things. So the spatial resolution of the EBSD is about to dash. Statement 1 says for high resolution imaging on nanograins. Statement 2 says high performance FESEMs are required along with small samples. And statement 3 says short working distance. So all of these statements are correct because for high spatial resolution you need to have short working distance, you need to have small samples, and high performance field emission SCMs. Field emission SCMs will give you very high quality image, and for high resolution imaging on the nanograins. So in this case option D is the correct answer, where all the statements are correct for this spatial resolution of your EBSD patterns. The third question says, what is the first step for sample preparation for the EBSD measurement? For the EBSD measurement, first option says that sectioning, mounting, grinding or mechanical polishing. So firstly, sectioning will be done. So in sectioning, after that, is there any comment? Yes, Gautam, you are very correct. So firstly, sectioning will be done. The first step for the sample preparation of your EBSD measurement will be sampling. Sectioning, sorry. So the fourth question says, on what factors do the intensity of secondary electrons depend upon? So first statement says that the shape of irradiated object. Okay. Statement 2 says the chemical composition of the irradiated object. And statement 3 says the number of electron ejected. So the intensity of secondary electrons. This I guess many of you or all of you should answer this question. The intensity of secondary electron will depend upon what factors? Statement 1, 2, 3 or all? Anyone? Gautam says 1 and 2. Why not 3? Why 1 and 2? Can you explain? Anyone else wanted to try this question? This we have discussed multiple times. On what factors do the intensity of secondary electron will depend upon? The shape of object, the chemical composition of the object, and the number of electrons ejected. Which of these statement is correct? So in this case, if nobody is answering, less. Why are you not willing to try this question? This we have discussed multiple times. The intensity of secondary electrons. So the secondary electrons will depend upon the shape of irradiated object, because this basically tells you about the topographic information, the chemical composition of the irradiated object. So if your specimen is having a higher atomic number or lower atomic number, then your intensity will depend upon the chemical composition and also basically the number of electrons which are ejected by the electron. So Gautam said 1 and 2 statement, but statement 3 is also seems to be correct. So according to me, option D, all 1, 2 and 3 should be the correct statement for this question. The intensity of electrons will be governed by the chemical composition, will be governed by the shape of your specimen, and will also be governed by the number of electrons which are being ejected from your specimen. Is this question clear to you, Gautam, now, or you still have doubt? Okay. Then we'll move towards the next question, question number 5, which says an accelerating voltage of 20 kilovolt applied to a tungsten filament in SEM. What could be the wavelength of electron? So here this is a numerical question, so I'll try to write it down. So basically the accelerating voltage is given by 20 kilovolt, and you need to find out what is the wavelength of electron. The wavelength of electron basically, I guess we have discussed in our previous classes, most of the in the initial classes, where energy is given by half m v square, and if I wanted to write it in terms of momentum, then it will be small p divided by 2m, and the energy is also given as EV. V is your potential. So using this energy equations, we can have our wavelength lambda is equal to h, where h is your Planck constant, divided by under root of 2 m mass of electron, E which is charge of electron, and V is your potential. So all these things are constant. H Planck constant under root 2 me. M is mass of electron, which is basically 9.1 into 10 raised to the minus 31, and E is your charge of electron, which is 1.6 into 10 raised to the minus 19, and your Planck constant will be 6.626 into 10 raised to the minus 34. And if you will do all these things, you will have on an average, sorry, 150 divided by voltage whole to the power 1 by 2. So this will give you wavelength in terms of Armstrong. So basically in this question you have given the voltage as 20 kilovolt. So can anybody tell me what will be the wavelength by using this formula, that lambda is equal to 150 divided by V whole raised to power half. This will give you lambda in terms of Armstrong. Anybody can calculate it and tell me?
And it's coming 0.0
0086 nanometer.
Yeah, I couldn't hear you. Can you please repeat?
Ma'am, it's coming 0.0086 nanometer.
Yeah. So the option C is most close to that. So option C will be the correct option. But uh, this is where you are taking your relative mass of your electron. But when you are taking, uh, just a second. But when you are not considering your relative mass, then you can also write your wavelength as lambda is equal to simply 1 point, or you can write 15 divided by under root of V. So if you are writing 15, it will be in Armstrong. And if you calculate using this formula, what wavelength you will get? Can you calculate it now?
That will come 0.0106 nanometer.
Yeah, so depending upon the equation, we are taking relativistic mass or not, you can have different wavelength values. So from one, you are getting this 0.0086, and from other, you are getting this 0.0106. So this is not 0.0086. So I guess they will be considering this equation only, because this is not 0.86 and they have mentioned to correct up to 3 decimal point only. So I both these can be correct depending upon the equation which you are using. You are using either relativistic mass of your electron or just the normal mass of electron. So according to the equation, according to the mass of electron which you are using, you can have either option B or option C as the correct statement. Since I guess since the fourth decimal is not correct in the option C, so you can correct option B in this case. So the next question says, what is the steps necessary to produce the EBSD patterns in SCM? So the steps which are required for the EBSD pattern in SCM will be, the statement 1 says that tilt the specimen so that its surface makes an angle of about 70 degree with the horizontal. This statement is absolutely correct. The statement 2 says turn off the scan coils to obtain a stationary electron beam, and statement 3 says place a recording medium in front of the tilted specimen to capture the diffraction pattern, which is known as the phosphor screen. This statement is also correct. We have seen in the diagram where the phosphor screen was placed at a certain distance from your specimen, and the statement 2 is also correct. Then you need to turn off the scanning coils to obtain the stationary electron beam. After the firstly the tilting will be done, then you need to turn off the scanning coils to obtain the stationary coils, and then your Kikuchi patterns will be formed on this phosphorus screen, which is placed at a certain distance from your specimen. So in this case, option D, all of the statements 1, 2 and 3 will be the correct option. Any doubt till now? Everything is clear to everyone? Any doubt to anyone till now? Okay. Then we'll move towards the next question. Let me select the pointer. The next question says, question number 7, and in an electron microscope, the electron beam of wavelength 0.0061 nanometer passes through an electromagnetic lens having a strength of 0.6 Tesla. Calculate the radius of electron beam. Since we already discussed the relation, so basically what this question says, that they have an electron beam and the wavelength of the electron beam is given of the, and you have your magnetic field of 0.6 Tesla. You need to calculate the radius of electron beam. Firstly, I request all of you to please calculate the energy in kilovolt of the electron beam. It is given as the wavelength of 0.0061 nanometer. Since we already discussed in the previous question about how to calculate the wavelength from energy, can you calculate the energy from the wavelength which is given over here? I'll give you 2 minutes. Can you please calculate and tell me? Everyone, please try it. We discussed this in question number 5 over here. Please try to calculate the energy of electron using this wavelength and using the concept which we discussed in question number 5. Anyone? You just need to use the formula which we discussed in question number 5 to calculate the energy of electron using the wavelength as 0.0061 nanometer, which is given in your question number 7. Anyone is not able to calculate it? Why? I'll write the formula once again. Please try, please. The lambda will be given by 150 by V whole to the power half, and here the lambda is in Armstrong. Please remember it. Now your one lambda is given. You need to calculate the volt energy in volt or kilovolt. Please calculate it using this formula and let me know. Anyone? You can tell me the voltage in kilovolt term itself.
Voltage is 40.311 kilovolt.
Yeah, who is this? Only she is answering. Rest all are. What's your good name?
Adrija.
Okay. So why are not anyone else is trying? Amjad says option C is the correct. We are till now calculating the voltage, Amjad. The energy of the electron. We haven't reached to the radius. I was asking about the voltage. So you also calculated firstly the voltage and then you come out to with the to calculate the radius of the electron beam, right? Okay. Rest all, please try to solve it. I wanted to hear from each every one of you the answer of next part. So this you can say on an average will be 40 kilovolt. Okay. And the next they have asked to calculate the radius of electron beam. And we know that the radius of electron beam R naught will be given by 1 by B magnetic field, which will be given in Tesla, into under root of 2 m V naught divided by E. Everyone, please try to solve this. So this is basically the formula to calculate the radius of electron beam, which is given by 1 by B, where B is your magnetic field, which has a unit of Tesla and which is given as 0.6 Tesla, and then into under root of 2 m V naught divided by E, where m is your mass of electron. And please listen carefully that mass of electron will be 9.1 into 10 raised to power minus 31, and your V naught you have already calculated as 40 kilovolt, and your E is the charge of electron, which is 1.6 into 10 raised to power minus 19. So I have provided you all the values starting from B to mass of electron, charge of electron, and voltage. You just need to put all these values in this equation and then you will be able to calculate your R naught value. Please calculate it, everyone. I request everyone to please try to put all these value in this simple equation and then please calculate the value of R naught. Everyone, please try. I'll give 2 minutes. Anyone? No one is able to do. R naught is equal to 1 divided by 0.6 under root of 2 into 9.1 into 10 raised to power minus 31 into 40,000 divided by charge of electron, which is 1.6 into 10 raised to the power minus 19. So after solving these under root terms, you will get 1 divided by 0.6 into 674.5 into 10 raised to the power minus 6. So this will give you, I'll write it here, this you will division will give you 1124.16 into 10 raised to power minus 6. So if you wanted to move this decimal point towards left hand side, that means you are dividing it, and you also need to multiply, then you will get 1.124 into 10 raised to power minus 3. So minus 3 will be basically your mm. So if you will remove minus 3, you will get simply 1.124 sorry. One to 4 millimeter. So option C will be the correct answer, which Amjad told you. Is this clear to now? Is this clear to everyone now? So firstly, your voltage is calculated using the wavelength, which is given as 0.0061 nanometer. And let me take the pointer now. So using this formula, lambda is equal to 150 divided by V whole raised to power 1 by 2, which gives you lambda in terms of Armstrong. Using this formula, you calculate, this is not equal to 14. Let me make it clear. Delete it. This gives your voltage as 40 kV, and after that, when you get your energy in terms of kV, then you can use this formula where your radius of electron beam R0 is given as 1 by B into under root of 2m V0 divided by E, where m is your mass of electron, E is your charge of electron, and V is your voltage, energy in volts, and your B is your magnetic field in terms of Tesla, which is given as 0.6 Tesla. So we just need to put all these values as 0.06 into under root of 2 into 9.1 into 10 raised to power minus 31 into voltage as 40,000 divided by charge of electron, which is 1.6 into 10 raised to power minus 19. So if you will solve this under root term, you will get 674 divided into 0.5 into 10 raised to power minus 6, and when you divide this 674 divided by 0.6, you will get 1124.16 into 10 raised to power minus 6, and by moving the decimal after 1, you will get 1.124 into 10 raised to power minus 3, which you can write as 1.124, and the unit from meter will change to millimeter. So option C will be the correct answer for this question. Any doubts or any comments for this question? This was very simple question. I asked all of you to solve it. VT Kumar also solved it and gave the answer as option C. Yes, you are correct. Why all of you are not responding? This was such a simple question to answer, no? I provided you all the values. So we should move to next question now. Question number 8, which says that the primary electron beam current is 1.5 microampere and the secondary electron current signal is 0.4 microampere and the backscattered electron current is 0.6 microampere. What will be the sample current, secondary and backscattered electron yield? So we discussed, I guess, this in the last lecture where we discussed about the secondary electron coefficient and back secondary electron coefficient. So the back secondary electron coefficient is given by the neta, which is basically the current of BSC divided by the beam current, which you can give by I naught. So your backscattered electron current is given as 0.6 microampere and your beam current is given as 1.5 microampere. So can you calculate it now and tell me what will be the back secondary electron yield? Yeah, so it will be 0.4. And to calculate your secondary electron yield, that will be given as delta, which will be given as the current of secondary electron divided by your beam current. So here it will be 0.4 divided by 1.5. Can anybody calculate and tell me? Yeah, it comes around 0.26, but there is no option as such of 0.26. But for back secondary electron they have provided 0.4 in option A and in option B. So I don't it was 0.26. So I don't know. In this one, your back secondary electron is 0.4, but your secondary electron should be 0.26. So using this option A and option B says 1.5, which can't be true because your beam current is also 1.5 only. So your secondary electron yield cannot be equal to that. So you can correct option B, I guess, which is 0.5 microampere. Huh? Sample current, but that option is also not given, no? Okay, sample current you are saying. Okay, then there is my mistake. Okay, sorry. Because, yeah, sorry. Thank you. So basically, your total current, your beam current is given by the sum of your backscattered electron, BSC. I thought they have asked about the secondary electron and backscattered electron yield. There was confusion from my side, sorry to all. So the beam current will be given by the sum of back secondary electron plus the sum of secondary electrons plus the sample current, which I'll write as IS. So your beam current is 1.5. Sorry. And your backscattered electron is given as 0.6. And your secondary electron current is given as 0.4. then you will be able to calculate your sample current. So that will come as, this will be 1, and then 1.5 minus 1 will be 0.5. So then option B will be the correct answer. That is, the sample current will be 0.5 microampere and the backscattered electron yield as we calculated earlier was 0.4. So here, thank you to you, and here option B will be the correct answer for this question. Any doubts? I thought they have asked about the secondary and then the backscattered electron yield. That's why I was confused. But if they have asked about the sample current, then you can calculate it using this formula, which will come around 0.5 microampere, and your back secondary electron yield will be 0.6 divided by 1.5 will be 0.4. And the next question, question number 9, says that the angular accuracy of EBSD. So the angular accuracy of EBSD is from 0.5 to 1 degree only. So option A is the correct answer for this question. Question number 10 says that the Kikuchi lines consist of an dash in a diffraction pattern, a excess line, a deficient line, both of the above, or reflected line. Anyone can answer this question? We discussed it in the today's class. Yeah, one will be the excess line and one will be the deficient line. Someone have also mentioned in the comments also. So in this case, option C, both of the above, that is the excess line and the deficient line, are present in the Kikuchi line. Then I have certain other questions which we will try, and then we will understand about the EBSD much more clearly. So choose the correct option. These, I have some statements and where you need to tell which statement is correct, and either it is the explanation of the previous one or not. So statement 1 says that the channeling contrast comes due to the backscattered electrons. So this is basically the channeling contrast which is coming due to the backscattered electrons. So this statement is very much correct. And the statement 2 says that the backscattered electron coefficient is dependent on the orientation of a crystal with respect to the electron beam. So this statement is also very much correct, that the backscattered electron coefficient neta will be dependent on the orientation of the crystal, because orientation of crystal will tell you how much electrons are being ejected with respect to the electron beam. So the channeling contrast comes due to the backscattered electrons. So statement 1 and statement 2 both are correct. So is the statement 2 the explanation of statement 1 or not? Yes, it is the explanation for statement 1, because yes, option C is the correct answer in this case. Thank you. Now people are paying attention, I guess. Yeah, so statement 1 is also correct. That is, the channeling contrast comes due to the backscattered electrons, and this is explained by the statement 2, which says that the backscattered electron coefficient is dependent on the orientation of crystal with respect to the electron beam. So so 1 and 2 both are correct, and 2 is the correct explanation of statement 1. So the next question says the same, that choose the correct option. Statement 1 says that the step size in EBSD should be less than the grain size. This statement is correct, very much correct. Statement 2 says that each grain gives particular orientation. Yes, this is also correct. To find out the misorientation and everything, only we use this EBSD technique. So each grain gives a particular orientation. This is also correct. So is the statement 2 the explanation of 1, or it is just that both the statements are correct and nothing explained by the statement 2. Any comments? Yeah. So here option D is the correct answer, which says both statement 1 and statement 2 are correct, but not the correct explanation of statement 1. Someone has mentioned, let me check. Yes, Rajesh also says option D. You all are very much correct. I guess you understand now about the EBSD and everything. So, statement 1 says that the step size in EBSD should be less than the grain size. This statement is very much correct, because if the step size is more than the grain size, then we will not be able to resolve the things more clearly. And statement 2 says that each grain gives particular orientation. This statement is also very much correct, but this is not the explanation for statement 1. So option D, that statement 1 and statement 2 both are correct, but statement 2 is not the correct explanation of statement 1. So option D is the correct answer for the question number 2 in this. So the last question, the third question says choose the correct option. Statement 1 says that the EBSD is not a bulk characterization technique for texture determination. This statement is correct or false? This is completely correct, because this it will tell you only about the surface, about 20 nanometer deep surface, not about the bulk characterization. And statement 2 says that the XRD is a bulk characterization technique for the texture determination. This statement is also very correct, because for the bulk sample information we use XRD, and the EBSD is used for the surface things only. So according to you people, which option should be correct? That option C or option D? That means both 1 and 2 statements are correct, that we all know, but is the statement 2 the correct explanation of 1 or not? Anyone? Rajesh says option D, that the statement 2 does not explain about the statement 1. Anyone else? Anyone else? Yes, Rajesh is absolutely correct. Option D is the correct answer for the question number 3rd, which says, sorry, the first statement is correct, that EBSD is not a bulk characterization technique for texture determination. And statement 2 is also correct, that XRD is a bulk characterization technique for texture determination. But this tells only about the XRD. It is not telling why EBSD is not a bulk characterization. So according to this, option D is the correct answer, which says that statement 1 and statement 2 both are correct, but statement 2 is not the correct explanation of statement 1. So then we'll move towards the last question for today's lecture, which says which of the following statement is correct with respect to the Kikuchi lines. This all of you should try to answer. Statement 1, only one of the statement is correct. You need to tell which statement is correct. Statement 1 says that about the Kikuchi lines. Statement 1 says that Kikuchi lines are formed due to inelastic scattered electrons followed by elastic scattering. Statement 2 says that the Kikuchi lines are formed due to elastic scattered electrons followed by inelastic scattering. And statement 3 says that the Kikuchi lines are formed due to inelastic scattered electrons only. And statement 4 says that the Kikuchi lines are formed due to elastic scattered electrons only. This we discussed in today's lecture. So I guess most of you should be able to answer if you were hearing to the brief discussion which we did before the questions. Anyone? Kikuchi lines are formed either due to, huh? Yeah. So she says statement 1. Does everyone agrees with her that these are the Kikuchi lines are formed due to the inelastic scattered electrons followed by the elastic scattering? Anyone else? Any comments? This I guess we discussed in our previous slides only. The first one only, which says that the Kikuchi lines are formed by the inelastic scattered electrons, which can be subsequently be elastically scattered, which will produce the Kikuchi lines. So according to this, only statement 1, so that means option A will be the correct answer for this question, which says that the Kikuchi lines are formed due to inelastic scattered electrons followed by the elastic scattering. This is the combination of both the elastic and inelastic thing. Any doubts, any comments for today's lecture? Only few people were paying attention in today's class. Do you have any doubts or any comments for your EBSD, or everything is clear to you? Any doubts to anyone? Do any one of you have any doubts or any comments for today's lecture or any previous lecture? Gautam and Nitin, do you have any doubts or any comments? Okay, thank you, Nitin. Gautam, are you still there? Gautam, are you there or have you left the meeting unattended? If you have any doubt, do let me know. If no, you can leave the meeting. You are not responding. I'll close then today's class. We'll meet in next class. If you have any doubt, do let me know over there. Okay.